To be honest, I haven't read this in detail.
So why is a vector of Lagrange multipliers?
Yeah, why is a multiplier? It's Lagrangian multiplier.
Is it a constant or is it a vector?
It's variables.
Series of variables.
Yes, a variable.
That's how big is that rank? Do you drive them on the fly? Or?
This is a scalar. For example, yeah, from a zero to the
So you got a scalar from Lagrange multipliers.
Okay.
And then you converge as A and E get closer to D. Is that what you mean? So while
Yes.
not converge, do.
Yes. Yes.
But is this convex problem?
Yeah, this is a convex problem.
No, the original one is
Original.
convex.
This is why subject to P plot this one, okay?
Yeah, but I mean, no. My question is this original optimization problem convex?
No.
But then how do you? I mean, then you apply this Lagrange multiply. Then I mean, the dual and the
So you convert this one to a dual problem.
the dual problem. I mean, they're not equivalent if this is not convex.
We don't need so this is not the equivalent. What we want is to get A and E. We don't need its equivalent.
Okay.
Okay, right? Of course, this is a approximation. It cannot be. Of course, if you do, this one, I believe the solution cannot be exactly the same as the solution if you use this one directly. All right. Okay.
So if I got this right, what you do is you sort of use Lagrange multipliers to come up with a new E. Do the singular value decomposition on D minus E plus mu, whatever that is. That makes things a little bit better, but not much. And so you
Yeah. Do it again. Yeah.
So this thing is a dog. On any reasonable size data, this takes forever. Am I right or not? The center here loop is an SVD, which is really expensive.
Yes. Yeah. It is possible. It is possible.
It's possible, but it just takes a long time to compute.
Yes. Yes.
Yeah, cool. Thank you.
Can I move on? Don't ask me anymore.
No, sir. Thank you. No, that's
I'm joking. Right? Now, so we know why is a robot. Okay, in this paper article, okay, actually the manuscript was submitted in 2009, okay, but it's published in 2011. There's a proof for this robustness. Okay, so this E can be arbitrary corruption. So given the corruption, so this it has proven, okay, A can be totally recovered. Well, so why there's two sides of one coin? If this argument is applied to denoising only, that's fine. All right. Okay. So we can recover the A, right? And we can denoise. So we can totally pick up A from E. But if you want to apply opposite, the other application, for example, classification. For example, what I'm doing is video surveillance, and also ToCAI will apply this to. I hope you can to document analysis. Okay. For example, for video surveillance, why not we treat A as background, okay, E as a moving foreground. Okay, this is a constant something. Okay, so this means variation, right? So A and E, and for document analysis, A stand for those common words, okay, appearing in all documents. This E stands for some salient word, the keywords, particularly distinguish this document from others, right? So if we apply opposite, actually this is tricky. Actually, although A can be recovered, actually in those video surveillance or document analysis, E is our objective interest. We don't really care about this A, right? Actually here, the so-called noise all contained in E, right? Okay. So for safety, okay, A is very clean, okay, or can be recovered arbitrarily from arbitrary corruption. But actually, all the noise goes to this part, right? Actually, it's quite reasonable. Right? So,
Sorry, I don't quite understand why whether A can be recovered. It depends on the application. So you said
for this method, okay, this RPC method, it doesn't care about any application. Give me data, okay. I can only find out some data, okay. Very clean, okay, all right. No. So whatever noise is, I can pick it up. Right? So give that for example, a face image with mark, cat, car. Whatever, it's very robust, okay? Whatever errors, any wrong collection, I can recover this real face images.
Okay.
Alright? Okay, this is it, okay?
So the rest is E, but what is the problem?
Well, okay, if we want to use this RPCA for other applications, alright? Now, for example, for application with no noise, no noise, okay? So this error, not really noise, not noise at all, actually, but the variation. Now, for example, for face image, okay? Today I look like this, okay? Tomorrow I look different, okay? Maybe tomorrow I have some pimples, okay? It looks so different, but still me, all right? Still me, not really error, not really noise, okay? All right. So then it doesn't really work. It's not really robust. All right. You cannot. Okay. It is possible if you really apply this RPCA. So you just kick that face image out. But you can treat this one as noise. All right. Okay. And also, first, another two reasons. Actually, in some applications, we don't have really noise. Second, we want to apply RPCA for other applications. For example, video surveillance or document analysis, because we want to make use of the properties of RPCA, okay, which can separate data into two parts. One is actually stable one, okay. One is the unstable, variational. That's it, right? And so actually here this noise, the so-called noise, right, can be actually a bias for the data, okay, which can actually is the key point to distinguish this data from others. Right? So in robust PCA, it doesn't care about any real noise. Okay. So in my experiment, I tried to introduce real noise, okay, for some application. For example, video surveillance. So we still use those sparse error and some error, very common and assumed to be in any application. For example, a Gaussian noise. So this is called dual noise, still with the same technique of Lagrangian solution. We just have this one different, but we use a different norm. It's a Frobenius norm. The others are the same, right? They're all the same. Okay, use this is the initialization and iterative SVD. All right. So we can separate the data with a sparse error as well as Gaussian noise. So this is for the video. We can separate the background with the moving foreground. We did some comparison between the original RPCA with ALM algorithm and the dual noise. We can see this one can improve the accuracy, but pay the price of time. Okay, so this one takes numbers so high for this. Okay, pay price of speed for accuracy.
So what is M? What is M? So the rank of P set as 0.1 M. What is M?
M is some parameter, okay? Some parameter in at the programming level, okay? At the programming level. So, any question? I'm going to draw a conclusion. Just like, don't forget that. Middle 6 is not 6, right? Our PCA is not PCA, okay? You believe the format, then believe the letter, okay? Our PCA is not a PCA at all. So, for the motivation, actually PCA is motivated by dimension reduction and orthogonal transformation. And later on, PCA is applied to classification, cluster regression, right? And in the applications, we have found some problems, okay? The sensitivity to noise. So that we actually, there are lots of researchers doing lots of research, not just this robust PCA, okay, to make PCA robust. Right? So robust PCA is actually look at the problem from a subspace view. Okay, the data in the original space, actually the data is only covers only a very small number of subspaces. Right? So and also robust PCA, the motivation is not for dimension reduction, okay, or not orthogonal transform. Okay, the motivation is for especially for clustering. Okay, so when PCA is applied to clustering, there's a problem, okay, with sensitivity. That's why people investigated RPCA from a subspace view. So RPCA is a subspace approach. And there are also problem with RPCA, both PCA and RPCA. Because this is a subspace, right? And for some particular data, they may be covered, they may exist in multiple spaces. For example, apple. Apple is also a keyword, okay, of fruit. Can be electronics, okay. So in this case, of course, they can find a way, okay. They treat this one as a two classes or whatever, okay. So that's why. So in this recently, when people are doing RPCA, they find enough technique to improve the RPCA, which is a subspace cluster, which can allow any particular data belonging to multiple classes. This way, right? to deal with these cases. This is not about RPCA. I want to move further to explain where RPCA is. Okay, PCA, RPCA. I'm going to subspace clustering, okay, which is considered an advanced technique based on RPCA. Right? Just a brief view. So just now we said we want to make the rank as low as possible. And we know the rank, that means some intra-class data, can be represented by others. We haven't yet used this property. So any data can be expressed by itself. What does it mean? D equals D times C. Now, if C is identity matrix, no problem. But does it make any sense? It doesn't make any sense, right? If C both 0, it also this one will be actually, for example, 1 can be itself. But they may also this equation can be also hold for some other values of C. That's actually the same for rank, because the each entry can be represented by others. All right. Okay. So that's why it's called self-expressive. So based on this property, so the data can be D times C plus some bias error. Can we follow this robust PCA? So this A clean data, okay, can be also represented by the cell. So this is the way how to use low-rank representation. So this is maybe we can treat this as an advanced version of RPCA. Okay, they're called subspace cluster. That's it. PCA. Okay, this is the formula. Don't ask me anymore, I forgot. Okay, because it's suitable for classification and mostly for dimension reduction. Okay, it doesn't perform very well in clustering. For RPCA, because it's motivated by clustering. Okay, and subspace is almost for clustering only. Okay, for those actually noise outlier. Okay. If we have some this problem outlier or noise, we can think of either the linear function, okay, for example, RPCA or probabilistic framework. That's conclusion. Robust PCA is not a PCA. I think this is your last slide. Yes.
KPCA?
Kernel PCA. Kernel PCA.
I'm sorry?
Kernel PCA.
Kernel, so you project up to it. And Chris?
Any question?
So is robust PCA a PCA?
No. Like what I said.
I just want to make that clear. So, have you done a particular clustering benchmark? Have you done PCA, RPCA, and subclustering on that and shown that in fact you get this star? Is this just your feeling?
This is my personal view. Okay, this is my personal view. Totally my personal view.
Have you
cannot be published.
Run on a benchmark?
Huh?
If you run all three on a benchmark?
It makes okay. I can't, but it makes no sense. Okay, just maybe.
Well, I mean, then it's no longer just your feeling. There's evidence to support your feeling.
Yes. Not very. Okay, I just do this one to. I hope to make myself understood, to help you understand more on this PCR, PCA. Okay. I haven't proven. This is just based on my empirical knowledge. Of course, with some analysis.
I'm not assuming that so run on a benchmark, you don't prove it either. You just provide some evidence. That's all. I'm all for that. So that's the way we do. I was kind of hoping Roman would show up because Roman is quite into PCA. But I mean,
he's busy with babies.
Yeah, but he's got a 3-month-old. So yeah.
No, he's away. He's
All
in
right.
another country. He's in another country.
You just take the kid there. With the dad.
With the baby.
So
No, I don't think it's big.
So PCA and ICA, the independent component analysis, are quite closely related. We typically use independent component analysis for blind source separation. Yeah. So you've got 3 different voices in a room, and you want to figure out which voice. You get one signal, and you want to see which voice is which. Can you do
RPCA
on that?
I don't think so. Because this RPCA, the purpose to treat E as totally different from A. Okay, all right. So in that case, some equivalent components. I mean, equal.
Cool. So what's this D equals DC plus E? So so here what do you want to achieve? So you have D, then you want to compute this C and E, or?
No. Yes, we will get C and E. Okay. This is just my. I don't know if you were confused because this is just I want to move further. Okay. To explain the position of RPCA, okay? We say, for example, it's between PCA and subspace clustering, right? So the C is introduced to for optimization, okay? So this with D, so this each actually to find the lowest rank, actually we use this self-expression to get the lowest rank. That's the C.
But the C is given or
No.
then what's the constraint for C? The rank of C or
Yeah, the rank of okay, this one not really the rank. Okay, actually the C is that's why it allows because I didn't expand this. Okay, because we want to solve this problem. Okay, so you can see the C will be a block matrix. Okay, so this one as maybe this part. Okay, this part you keep this one part as low rank. For example, if the data belongs to 3 subspace at the same time.
But how do you know this? How do you know that the data belongs to this subspace?
We don't know. We don't know. So
then how do you format the C?
just for the optimization, because to achieve the optimization, so you will find out automatically.
Okay, so can you say that the constraint is like the dimension of the rank of C is 3, for example? I mean, if you are interested in like 3 dimension, then the rank of
Yeah, so this is a block matrix. Okay, so if you can find the real final solution, so this C will consist of 3 blocks. One with a rank of 2, okay. 2 just one rank, okay. So 3 blocks, the C, not just one matrix. 3 block matrix, okay. I just give you some terminology, okay. It's called subspace clustering, okay. This is I think this is really very new research, okay, called subspace clustering.
But there are many subspace clustering algorithms exist, and so how does the method you propose here differ from them or better the existing ones?
Currently, I'm not doing subspace clustering. Okay, I'm just doing RPC, not a subspace clustering. Okay, maybe I don't know, maybe 5 years or 10 years later.
I will August.
Not now. Okay, because you can see, there are a lot of like what you said. Actually, so theoretically speaking, it looks perfect, beautiful, right? Actually, there's actually no free lunch. Right? If you want to cover all these cases, okay, it makes your optimization very hard.
For example, if you have text data, right, often it's very sparse, and if you use some existing subspace clustering, you use it a priori to prune your tree, it can be quite fast. Whereas if you use this AC plus E, this is an optimization problem. So perhaps the computation is heavier than the existing ones, especially for text, because this is the field I'm working in.
Yes, it's time consuming.
Yeah.
Yes, it's time consuming.
So is it possible to first do some high-level subspace search and then apply something on top?
It depends. For example, for a search engine, if we will use this one for actually it can be divided into 2 states for this search engines. For offline learning, once new document come in, okay, we use there is a background software called Spider to look for every new document. Every new document, we find a new document, okay, maybe publish it last night. So in offline categorization, we can use tokens. It doesn't matter. It takes 24 hours as long as it can provide very accurate. So this document we can categorize. Okay, this document is linked to say because say it's sense spoken. If you can categorize this as accurate as possible, because this offline training doesn't matter how long it does it take, right? Okay.
Thanks very much.